In this short video, we'll talk about how to use different coordinate systems to more naturally represent regions that we're trying to integrate over, which ends up meaning that we have much simpler integrals. So let's take as an example integrating a triple integral to integrate the region inside of a sphere of radius 4. So this is a pretty nasty triple integral here. Certainly don't want to do it by hand here. But this is partly because this sphere is not very easily described in terms of x, y, and z, the x, y, z coordinate system. There's a much more natural way to describe a sphere, and that is using spherical coordinates. You'll remember the spherical coordinate transformation, t of rho theta phi equals rho cosine theta sine phi, rho sine theta sine phi, rho cosine phi. I would give that to you on a test, but you might remember this from problems 5.8 and 5.9, where we talked about using different coordinate systems to represent objects more naturally. So in spherical coordinates, representing this sphere, the region of this sphere becomes very simple. Rho goes between 0 and 4, the center of the sphere, out to the edge of the sphere. Theta goes all the way around, 0 to 2 pi. And phi, remember phi represents the angle with the positive z-axis. So here is phi equals 0, and all the way down, pointing down the negative z-axis, is phi equals pi. So phi, to get the whole sphere, the whole ball, the whole region, we have phi goes between 0 and pi. Those inequalities represent the entire sphere in spherical coordinates. And so we can set up a triple integral using spherical coordinates. d rho, d theta, d phi. Rho goes between 0 and 4. Theta goes between 0 and 2 pi. Phi goes between 0 and pi. The one thing we're missing now still is that d rho, d theta, d phi, when you transform back to dx, y, dz, may be stretched or shrunk. So we need to multiply by the Jacobian. And remember, the Jacobian here is given by taking this transformation, taking its derivative, which gives us a 3 by 3 matrix, then taking the determinant of that, and then taking the absolute value of that. And if we do that and do the simplifications, we'll get that this Jacobian is the absolute value of rho squared sine phi. And notice our phi goes from 0 to pi. If phi is between 0 and pi, then sine of phi will be positive. Rho squared is always positive, so we can drop the absolute value signs here in our problem. And so we get rho squared sine phi. And so we get that this integral is equal to this really nasty integral up here. I'd much rather do this integral down here. The problem is much more naturally described in terms of spherical coordinates. Now let's look at another problem. Let's look at the integrating over the volume underneath 9 minus x squared minus y squared, and above the xy plane, above z equals 0. So if we set up a xyz integral for this, we'd end up with something that still is pretty nasty. Ugh. But there's a more natural way to describe this that takes advantage of the shape having symmetry around the z-axis, rotational symmetry around the z-axis. And let's use spherical or cylindrical coordinates. So you'll recall the cylindrical coordinate transformation is sort of like the polar coordinate transformation. It's r cosine theta, r sine theta, z. And using cylindrical coordinates, we can describe this region as, let's see, r goes between 0 and 3. That's 3 on the xy plane. And theta goes between 0 and 2 pi. It goes all the way around. This captures the rotational symmetry around the z-axis. And then z is going to be 0 on the bottom, and on the top it's going to be 9 minus x squared minus y squared. But we don't want any x's and y's in our polar coordinate integral. So we'll recall that x squared plus y squared is equal to r squared in polar coordinates. So 9 minus x squared minus y squared becomes 9 minus r squared. And so our cylindrical coordinate integral becomes, I guess we'll keep the same order here, dz, d theta, dr. R goes between 0 and 3, theta goes between 0 and 2 pi, and z goes between 0 and 9 minus r squared. And don't forget the Jacobian here. The dz, d theta, dr gets stretched or shrunk. That little tiny infinitely sort of small box gets stretched or shrunk. And we'll go back to xyz plane, or xyz coordinates. And how much does it get stretched or shrunk by? That is the Jacobian. So we take, again, the determinant of the transformation, the determinant of the derivative of the transformation, and take the absolute value of that. And if we do this and do the simplifications, we get that's equal to r. And again, r is 0 to 3. It's never negative, so we can drop the absolute values in this case. And so we get this integral right here. Much, much nicer than this rectangular integral, this xyz integral up here. So the basic idea, express your region in the new coordinate system, set up the integral using bounds in the new coordinate system, the variables in the new coordinate system, and make sure to multiply by the Jacobian, so that when you calculate the volume of this little tiny box, multiply it by the stretch factor, you get the volume of a box in the xyz coordinate system. Again, 12.8 through 12.14 are the problems that deal with this. You might find it useful to go back to chapter 5, like 5.8 and 5.9, where we dealt with this, dealt with thinking about regions and other coordinate systems before.